right, so moving on to our next speaker, building profit and resilience with a biological approach to nutrient management. Our next speaker will be Brian Dougherty. Brian is a regenerative agriculture consultant for the Understanding Ag and a student of the soil. His roots are planted in northeast Iowa, where he manages a family dairy farm. He is now a partner at Wild Type Ranch, where they produce direct-to-consumer pasture, meat, and eggs. He applies his passion for working with nature and his background as a farmer and agriculture engineer to help heal broken nutrients, water, and energy cycles to make regenerative food production a reality and make farming fun again. Brian's presentation today will focus on biological approach to soil nutrient management. Welcome, Brian.
Great, yeah, appreciate the chance to be here. I heard early March is a lovely time to visit the island, so appreciate the timing on the conference here. But no, it's great to be here. Never been to this part of the world before, so really appreciate the invite. So I really want to kind of challenge you to think a little bit differently about nutrient management. We'll kind of get into that as I go here, but first, just as an American, I need to clear the air on the tariffs here. So, I had to prepare the proper documents for my travel, so hopefully I got everything covered here. But just want to say on behalf of Americans, we haven't all completely lost our mind yet. So appreciate that nobody's punched me yet. So I'm going to talk a little bit about, just briefly up front, like why do we need to do things differently? Why can't we just keep doing what we're doing? And then get into improving biological function in soils and more of a systems approach that can be more resilient in the long run. So why do we need a different approach? You've maybe seen this graph before. This is actually Canada data, cuts off in 2016, but we see the same thing in the States. Costs continue to go up, gross revenue is going up, net profit, not so much. We're not making any more money than we did back in World War II. So net farm income was higher, 80 years ago than today. And the price of fossil fuels, machinery, if you're farming, how many farmers in here? Got some? Yeah. So what's happening with machinery and input costs and everything just continues to go up. Been increasing faster than the consumer price index since the 1950s. So we're just constantly trying to swim upstream. So pesticide use, just another example here, and you see the same thing if I put up a graph of herbicide-resistant weeds or anything like that. So we've basically doubled pesticide use globally in the last 30 years on less farmland, but somebody forgot to tell the bugs because the amount of damage, from crop pests is basically unchanged. And I don't know how you're all doing here, but in the States, we're doing a pretty bang-up job of getting cancer and all kinds of other things. I'm not saying that's all related to pesticides. There's lots of other things. There's plastics and all kinds of other stuff that's contributing to that, but this is certainly a factor. We know some of these products are carcinogens. So what we're doing is not working currently. And we can keep kind of trying to push on this rope, but it's getting more and more challenging every year. So currently, our food system is not doing so great. You're all, I'm sure, aware of this. Organic matter loss, erosion loss. I looked up PEI. Most of the island looks like still considered at moderate risk for soil erosion, 11 to 22 tons per hectare. We're probably in about the same place in the upper Midwest. We've lost a lot of crop diversity. We've lost beneficial insects. We've got herbicide-resistant weeds. Nutrient density, and what we just call kind of the Western diet, it's essentially making us fat and malnourished at the same time. So it's not going well. There's, that's more of a processing issue with ultra-processed foods and things, but that's all part of our food system that we're trying to change. So some of the challenges I see, I travel all over the upper Midwest, East Coast, West Coast, kind of all over the States, then a little bit in Canada, and I see this everywhere I go. So the first one is compaction. Soils just cannot breathe. We can't get oxygen into the soil. Second, I just call a broken water cycle. Basically, we can't get our water to infiltrate because the soil is compacted. So then we get extremes, temperature extremes, moisture extremes. The third, again, would be over-reliance on pesticides. And again, that's mainly because our soil doesn't function very well. So then we step in with these tools to try to get things to work better. Number 4 would be poor nutrient management. Same reason. Soil's not cycling nutrients like it should, so then we have to step in and apply a product to try to make up the difference. We just say, the soil's constipated, or, Iowa, where I'm from, we've got huge nitrate leaching issues. That's kind of like the soil having diarrhea, essentially. Number 5, lack of carbon. Carbon is the food source for microbes. That's what makes the world go around. Our soils, a lot of them are starving to death. There's not enough microbe food. And then number 6, because of that lack of biological activity, it's really the biology. That's what I'm going to hammer on over and over today. It's the biology that's driving the train, or that should be. So, and if it's not, our soils can't function properly. But I put this list together and I realized they're all related, they're all connected. 1 and 2 are just symptoms. Soil is not inherently compacted. It generally got that way because of our management. Now there's natural disasters and things like that cause compaction, sure, but generally soil should be fairly well aggregated. You go dig a hole in any kind of natural area or even the road ditch, it looks pretty decent. 3 and 4, those are reactions. That's what we do. It's what we call management. So we step in and try to fix the problem because of 1 and 2. But it's really number 5 and number 6 that are the problem. And unless and until we deal with 5 and 6, lack of carbon, lack of biological activity, we're always going to be fighting those first 4. So that's really the message I want to drive home here. So there's kind of this old view of how soil functions. We recognized for a long time that there's chemical, physical, and biological components to the soil. But, when I started taking soils classes back in the early 90s, we really didn't put the pieces together. The chemical, we talked about NPK and, soil texture, physical. The soil was just kind of there to hold up the plant. We didn't really think a whole lot about what was going on. In the biology, if we talked about it at all, it was usually in the context of pests and diseases, right? If it moves, kill it. We don't want any creepy crawlies on our plant. But then we kind of learned more about this soil health thing and what's going on. And we came up with this. So chemical, physical, biological. How many of you have seen this graph before? If you've ever been to a soil health meeting, you've probably seen it. So this is kind of how we think about things now, and this thing we call soil health is where they overlap. So definitely a better way to think about soil, but I'm going to argue that this still completely misses the point. This is how we should think about soil. It is a biological system, and it's driven by carbon. The number 1, by far, most important physical characteristic of a soil is how well aggregated it is. And what builds aggregates? Biology is what builds aggregates. These chemical reactions, these are biochemical reactions. They're driven by the biology. So to me, soil health is biology and carbon. And if biology is not the dominant driver in your soil, it is completely dysfunctional and it's costing you money. So what is a functioning soil then? If dysfunction is the problem, what does a functioning soil look like? Well, kind of looks like chocolate cake. Well aggregated, rapid gas exchange, very resilient, resistant to erosion, minimal compaction, active microbial community, good nutrient cycling, minimal need to, use sides, they call them side effects, to, keep a healthy system going. So this is what we're after. This is a picture, I don't know if any of you know Blake Vince or not. He was an Nuffield scholar from Ontario, so I got the chance to go to his farm, took this picture. This is some pretty amazing aggregation, given the area that he's kind of dealing with there. I mean, this soil's so stable, it made it through a Canadian winter without therapy, so. Okay, you're laughing at my jokes. We're off to a good start. So how do we fix soil? We talk about understanding ag, we talk about the soil health principles, and we use 6, some people use 4, some people use 5. We're all talking about the same thing: context, minimize disturbance. That's one I think we need to change on here. It says do not disturb. Really, that should say optimize disturbance, because there's always disturbance in a cropping system. We're picking what type of disturbance we want to use. Is it going to be a herbicide? Is it going to be tillage? What are we going to do? But, this improves aggregation, it adds carbon, it feeds biology. If you go back to my list at the beginning, this is how we address all of those problems. It fixes our compaction. Now, that's easier said than done. I realize there's equipment issues and all that. We don't really have time to get into that today. But really, at the end of the day, the only way to deal with compaction in the long run is with a living root. So this is how we get there. It's really soil aggregation that's the engine. That's what makes soil work. That provides conditions for life in the soil, the water films for the biology to live in, both aerobic and anaerobic pockets. We think anaerobic is bad, right? Well, if it's completely anaerobic, yeah, that's bad. But what if you want to fix nitrogen? A lot of those organisms need anaerobic conditions. How do we get that? We get that inside these aggregates. You can have little anaerobic pockets right next to an aerobic pocket, right next to some water, right next to some nutrients. The root goes through there and it's got everything it needs. High and low pH, high and low redox potential, it's all there inside that aggregate. So when we think about cropping systems and how do we build more resilience and profit, I really like this idea. This is a professor at Western Sydney that came up with this, kind of a 3-step way to look at this. And the first one is efficiency. So this has kind of been around for decades, the 4R, nutrient management, inhibitors, reducing tillage, all good stuff, all things that we want everybody to be doing. This is getting us going in the right direction, but we're still treating symptoms here. This doesn't fix soil. It doesn't address those root causes. And if you just do this and stop, it's actually a barrier to progress. The second one is substitution. I work with a lot of producers that are doing this, so, different forms of nitrogen, amino acid types, humic acids, making your own biofertilizers, and there's lots of this stuff you can buy now. All good stuff. Basically, we're trying to reduce the usage of some of these, products and practices that are more damaging to our biology and substitute them with things that kind of help the biology, or at least don't inhibit it. So, very important step. But unless you're making this yourself, you're still writing a check. It's still an input, but it's an important step. The third one is redesign. This is basically implementing the 6 soil health principles, because this is what actually addresses the root cause of soil dysfunction. And it's really the only pathway to long-term resilience. The problem with this diagram here, the way this is laid out, it's actually backwards. Almost everybody, pretty much every farmer I work with, they start with number 1, dabble around with some stuff, then they go to number 2. It's like, well, maybe I can swap out a lower salt fertilizer or something like that. And then they finally, when they start seeing things working, they get serious about number 3. We really need to flip this on its head. We need to start with the principles first, because that will make number 1 and number 2 work better and work faster. And you'll see more benefits from it. So I just want to talk about carbon and water here for a minute, because they're super important. This is just a sketch I came up with on a carbon cycle for a 200 bushel corn crop. Y'all use like bushels and acres here. Hopefully you know what I'm talking about. I was in British Columbia a few months ago and I did my whole slideshow in metric, and I get up there, yeah, we do acres and all that stuff. So you're just as metrically confused as we are, I guess. But no, the point of this sketch isn't to focus on all the numbers. It's just to show that this is a flow. There's about 30,000 pounds of carbon being pulled into that crop every year. That's a lot of carbon. Where does it all go? It goes everywhere. It goes out through root exudates, respiration. This is a steady state system. If you add all those numbers up, nothing changes. You're not going to add organic matter. So our little box here at the bottom, our soil carbon, that's our organic matter. That's our storage tank, essentially. So if we want to make that number bigger, How do we do it? And where's the fertilizer truck? Who's out there adding carbon? Unless you're adding a lot of manure or a lot of compost, you're probably not adding any carbon, and that's totally fine. You don't have to add it, but if you're not going to add it, you better grow it. So we need more living roots. We need a new arrow going into our box here to add more carbon into the system, but then we need to not harvest that carbon off and remove it again. So that's how we improve this system over time. And the point I want to make here is this is all biology. It's biology that's driving almost 100% of this. And this is probably the most important cycle on your farm. So if we think about what's going on in the field, I mean, as a farmer, as an agronomist, you know, we hear all about CO2 in the atmosphere and global warming and all that. That's great, but I can't fix that. What I care about is what's happening in the field. We got any vegetable growers in here? Nobody brave enough to raise their hand, but I don't know how you get a tomato above ground, a potato below ground, the same plant. I haven't figured that out yet, but somebody figures that out, let me know. But no, we got CO2, plants photosynthesizing, it's making sugars, it pumps them out through the roots. We all know about this. What do the microbes do? They eat it, they consume it. They also need oxygen. Most of those are aerobic, just like we are. They need to be able to breathe, so they're consuming that. And then we get CO2 release from the soil. But the part that a lot of people miss on this is what's actually happening with that CO2. We think of it as being bad, but what this plant is actually doing, it's literally feeding itself. I mean, it's pretty incredible when you think about it. You know, the stomata on a plant leaf are on the bottom side. Why are they on the bottom side of the leaf? I mean, I'm not God, I didn't design it, but it just makes sense. Plants are designed to catch CO2 coming off of the soil, not trying to hoover whatever happens to be floating by out of the atmosphere. This makes your system more efficient. We need that soil to be producing CO2 so our plants can then catch it and feed themselves. This is why compaction is so detrimental, because what happens is you shut that whole process down, basically. The roots can't breathe, your water cycle breaks down, plants aren't happy, microbes aren't happy, now you're in a self-reinforcing negative downward cycle. So I think of aggregation, it's basically a survival mechanism for plants. Plants are actively trying to create aggregates. Just like we do, we move into a cold area, what do? You build a house because you want to stay warm. Plants are doing the same thing through building aggregates. It's a survival mechanism. So water, you know, you can argue which one's more important, carbon or water. They go hand in hand. They're just flip sides of the same coin. Just another simple sketch here. 30-inch rainfall environment. We're growing a corn crop. We've got evapotranspiration. So what's driving that? Both of my talks today, you only got to remember 4 words. A, B, C, D, aggregates, biology, carbon, and diversity. So any question I ask, the answer is one of them 4 words, probably. So what's driving this? It's biology, right? The B word. That's all being driven by the plant. What determines how much surface runoff you have? Well, how well aggregated is your soil? How much organic matter do you have? What determines that? Biology. What determines how much water your soil can hold? Well, that's how well aggregated it is. Pore space, organic matter, again, biology. So aggregation is just absolutely foundational for a functional water cycle to get our water into the soil and hold it. What determines precipitation? Nothing we can do about that one, right? No control over it. How many people think that's true? Somebody think there's no control? How many are just never going to raise your hand no matter what I ask you? Yeah, the rest of the crowd, that's what I figured. I appreciate you raising your hand. It's actually at least partially driven by biology. Plants create compounds they release into the atmosphere, volatile compounds. There's microbes that serve as the nuclei for raindrop formation. So over land areas, it's actually a significant portion of that is driven by biology, land cover. There was some research during looking back at the Dust Bowl, and they think that actually continued several years longer than it would have because we plowed up all the prairies and basically broke that biotic pump. We lost our plant's ability to do this. So are you going to do this on a quarter section? No. But if you got a couple 100,000 acres, now we're seeing some evidence that you can change these local microclimates, and you can definitely change it in the field. So getting into the nutrient management, this really requires some fairly, I don't want to say intensive management, but a different way of thinking about nutrient management. I just break this into 3 steps. Soil health principles, I already covered those. Figuring out what is limiting you productivity-wise, and then maximizing photosynthesis. And these all go hand in hand. There's no one more important than the other, and they all feed into each other. So there's really no prescriptions here. Somebody might throw something at me here, but for decades, our universities, I get it, I worked for a university, we like recipes. We like to look up numbers on a chart and tell us how much fertilizer to put on. I think we need to move beyond that. There's so much more going on in the soil than we understood even 10 or 15 years ago. Our fertility management needs to account for, if not benefit, soil biology. So number 1, following the soil health principles, to me that's all about just nurturing the soil food web, keeping the biology alive and letting it do its thing. So weaning off some of our inputs. This is probably going to sound completely nuts to a lot of people if you're an agronomist, but I think some of the fungicides, insecticides, seed treatments, we need to try to phase those out over time because they're inhibiting the biology in the root zone right when that plant germinates. We have people doing this and they're making it work. It can be done, and you don't have to be organic to do it. The next would be, trying to reduce some of the fertilizer inputs. I'll show a little bit of data on that later. Reducing herbicide rates, we're probably never going to get rid of them, but we all know that we've got all this herbicide resistance. We need to address this. We need some serious integrated pest management to get beyond that. So we've spent 200 years basically trying to administer beatings to the soil and hoping the morale improves. This approach really isn't working for us. Man, that joke fell flat. You have to take that out of the slideshow. So we got to stop the beatings. So number 2, factors that limit productivity. I would argue that in most cases, almost all, the number 1 priority limiting factor is air. The soil cannot breathe. We can't get air in the soil. If you can't get air in the soil, you're not going to fix nitrogen. You're going to limit productivity for sure. Second would be water. Again, air and water, same thing basically. They both come back to how well aggregated the soil is. The third would probably be decomposition. Our nutrients aren't cycling, our residues not breaking down. And then fourth, there could actually be some specific nutrient that's limiting productivity. But what do we do in the industry? We tend to jump right to number 4. Let's buy something and throw it at it and fix the problem. And we ignore the first 3. We've got to focus on the first 3 first, then figure out if we need to step in and add something on the back end. It's really the soil microbiome is what is limiting productivity. The biology just cannot function the way it needs to. Maximizing photosynthesis, number 3. This is all about continuous, diverse plant growth, keeping living roots in the soil, pumping carbon in the soil, feed the microbes. How do we maximize photosynthesis? It's in the basic equation you learned in probably junior high. What do you need for photosynthesis? CO2, water, sunlight. We can't affect sunlight. Can we affect CO2? I think we just covered that earlier. You can improve biological activity in your soil and you can get more CO2, which will then make photosynthesis more efficient. How do we get more water? We build aggregates. Again, biology. How do we capture more energy? That's just continuous roots. There's lots of crazy stuff people are playing around with intercropping and relay cropping and all kinds of things. Tougher to do in this environment. I get you're further north. But we've got to grow a bigger solar panel. We've got to keep that ground covered. And then number 4, there still could be some nutrient. There's lots of nutrients, especially our microbes, that are involved in photosynthesis in the plant, So that little arrow there represents a lot of super complicated stuff that happens in the plant, and you got to have all your nutrients to make that work. You know, manganese, there's all kinds of them. So there could be some nutrient. Again, we got to deal with those first three before we jump in and try to throw a nutrient at it. So there's just kind of this old view of how plants acquire nutrients. I'm not going to go through all this. You can pick up any soils textbook even today and you can see this stuff. You know, nutrients are taken up in the water, plant takes them in, they pump stuff across cell membranes, they can change pH. We've known about all this stuff for a long time. So, but these mechanisms, these are chemical, you know, some of this is biology as well, but this is mostly taking that chemistry view of how soil works. And even in a very inactive soil, this stuff will still happen. But I don't know who originally said this, but I think it made a lot of sense. You know, if you farm like your soil's dead, you're going to create dead soil. You know, there's a lot of truth to that. So there's this, you know, old idea, again, a lot of you have probably seen this if you've ever taken a soils class, you know, the barrel with the staves on it, Liebig's law of the minimum. It's not that this is wrong, it's just a very incomplete way of looking at what's happening in the soil. It ignores the role of biology, it ignores nutrient antagonisms. In fact, you know, it was recognized like 180 years ago that this wasn't really the full picture and that plants don't just get nutrients from the water. Anybody want to guess who way back then pointed out that this isn't quite right? It was the guy that came up with this, Justus von Liebig, in 1843. He said he was wrong, and that was the source of his foolish behavior, and 180 years later, it's still in soils textbooks. It's really the biology that's holding the barrel together in the first place, and that's the piece that we've kind of missed. So how do plants acquire nutrients? I just call it microbe farming. This is more of a new view. You know, now that we've got DNA testing and all kinds of cool stuff, learned a lot about the microbiome, the soil microbiome, the gut microbiome just in the last 10 to 15 years. We realize it's a whole lot more complicated than anybody ever thought. We know plants can take up organic nitrogen. I was taught in the 90s plants don't use organic nitrogen. We now know that's not true. It's not that those other mechanisms aren't happening. They all still are. They're just in a healthy soil, in a biologically active system, they're a smaller piece of the puzzle. We can get more of our nutrients through the biology, which is a more efficient way to do it. So if you farm like your soil is alive, you create living soil. How many of you have heard of the rhizophagy cycle? So if you have not heard of this, go home and Google it. I don't have time to get into all this, but what they discovered just under 10 years ago now, it's actually discovered in Australia, but Dr. James White in the States has done a lot of work on this. Plants are actually eating microbes. So I don't know if any of y'all are vegetarians or you got any friends that are, but I hate to break it to you, but plants are carnivores. They're eating microbes, they're cultivating them, they're farming them. So what they actually do is they pump carbon out the root tip. It says, come here, little microbe, and the bacteria come to the root tip and they eat them. They ingest them inside the root, they strip off the cell wall, and they use it for nutrition. But what's even crazier is some of the nuclei actually survive that process. For a long time, researchers couldn't figure out why those little root hairs on the side of roots were there. Well, they figured out that's actually the escape hatch for these nuclei. That root hair growth is triggered by bacteria living inside the root. So they build up in there, and then the plant launches them back out into the soil with a little squirt of root exudate, and they can reform their cell wall and go on their merry way or get eaten again. Plants are literally cultivating and farming and eating microbes, and we just figured this out less than 10 years ago. Every plant that they've ever tested does this. Now, how much is this happening in our row crops? We don't know. It's probably still a pretty small part, again, because we're not managing in a way to allow this to happen. But what if we did? How much nutrient uptake could we get through this? Nobody really knows. They think in natural systems it's somewhere around 70% of nutrient uptake is driven by this. I'm sure we're nowhere near that in crop fields, but we can do better. So we need to think about nutrient use efficiency as microbial efficiency. It tells us how healthy and functional your soil is. You all use the 4 Rs in Canada from what I understand, but how do we know what's right if we don't know what the biology is doing and we don't know what it's capable of? So to me, the 4 Rs are all about biology. I don't want to belabor it, but the right rate, time, place is whatever works for the biology. Our job is to feed the microbes, not try to feed the plant directly. The right source of nutrients is soil biology. Plants need to be getting their nutrients through the biology primarily, because that's a much more efficient way to do it, and we don't have all the environmental issues that we have. And the right way is within the context of the 6 principles. So getting into nitrogen, not going to get into the weeds on this, but there's a whole laundry list of different ways that plants can get nitrogen. There's this paper came out a few years ago. They said, nitrogen, it's like an emergent property of healthy soil. In other words, the healthier your soil is, the more respiration you have, the more aggregation you have, the more free nitrogen essentially you get from your soil, and the less you have to buy. So we need to utilize what we have. We run what's called the total nutrient digestion test. You can just run a total nitrogen test at the lab. You can get this number. You probably got somewhere between 5,000 and 10,000 pounds of nitrogen per acre in soils. It's all mostly bound up in your organic matter. So we have this huge pool. It's like a swimming pool like we got out here. So I'm going to grow corn. I'm going to throw 200 pounds of nitrogen into my pool. I'm going to harvest that corn, 200 bushel corn. It'll take up about 200 pounds of nitrogen, but it puts about 80 of it back in the residue. So I added 200. I removed 120. Where'd my 80 pounds of nitrogen go? Who knows, right? Might have leached, might have volatilized, might have denitrified. Where we want it to go is into our pool. We want to hold that and hang on to it for the next cropping season to make the system more efficient. We throw a cover crop in here. One of the things it does, our pool here has a leak in it. We call that nitrate leaching. Where I'm from, easily 15 to 25 pounds of nitrogen a year we're losing through tile lines, through leaching into our drinking water. We can help plug that leak with cover crops. So the way I think about adding nitrogen to crop ground, it's kind of like peeing in a swimming pool, right? It's like, it feels good, but it doesn't add a whole lot to the pool, and the public would be happier if we just quit doing it. That was a joke. It's okay, you can laugh. That one just sailed right over your head. So how do we make our pool bigger? That's the real question. We need carbon. We need diverse cover crops. We need to farm in a way that allows our free-living organisms, single-celled organisms, in the soil to fix nitrogen for us. I think they can do a lot more for us than what we're currently getting. We need to look at different forms of nitrogen. Nitrate is actually the least efficient for plants to use from an energy standpoint, because they got to burn up a lot of energy to take that nitrate and make a protein with it. Why not just let our plants eat bugs and get their nitrogen that way? That is a more efficient way to do it. So we need to focus on getting our nitrogen to cycle and not have to buy as much. Again, those free-living organisms, I haven't really seen any research on what they're capable of in a really healthy soil, but we just know anecdotally we don't have to apply as much nitrogen to those soils, so we know we're getting something. So nitrogen use efficiency, we really need to, where I'm from, I'm just using corn here as an example, we'd put on somewhere around 1 to 1.2 pounds of nitrogen per bushel. I'm working with growers that are down in the 0.6, 0.7 range, and they're not losing yield. They're doing this by fixing their soil, dealing with their compaction, building aggregates. So we can do this. We can do much better on these high nitrogen use crops, on making them more nitrogen efficient. Phosphorus, another example, here's a paper that came out maybe 2024. They looked at global meta-analysis. Only about 12% of applied phosphorus is actually used by the plant in that year. This is, pardon my French, this is pretty piss poor nitrogen use or phosphorus use efficiency. Nitrogen's maybe 20 to 40 depending on how and when you're applying it. This is not great. So most of it's just getting tied up in soil or getting lost or disappearing to who knows where. Again, you need biology, the B word, to access phosphorus. We're not going to get there just by throwing it on the soil. So this is an example from Iowa State University. I'm sure you've got similar data here, looking at soil test levels and relative grain yield, and you can see, yeah, at very low testing soils in the very low to low category, yeah, you get a nice bump from applying phosphorus. But I still see phosphorus recommendations all the time for people that got 30, 40, 50 parts per million, and they're still telling them to put on phosphorus. And I'm just like, you're not doing farmers any favors here. And even if you look at the data here, there's this weird thing. Why are there all these dots that are above the 100% line? That's all the trials that yielded higher without phosphorus applied. So we need to think about these things. I just call that the wasting money category. And if you look at all of this variability here, even in the very low category, we got some that there was a huge yield improvement, and there's some even in the very low category, it hardly did anything. This is mostly probably driven by biological variability in that field. So how can we do better on phosphorus? Again, we got to fix the soil. Focus on plant health. There's cover crops, different species we know can help with phosphorus. A lot of producers I'm working with are playing around with compost extracts and mycorrhizal inoculants, all these other things. Not saying you need to go buy bugs in a jug, but some of these things in the right context can be a benefit. Potassium, here's another one. This is just another meta-analysis. Dr. Mulvaney from University of Illinois kind of got crucified when this came out. Industry definitely didn't like what he said. But this is some data from the Morrow plots in Illinois. So they mined the soil essentially for 50 years. They grew continuous corn, and they put zero fertilizer on it. Now, it didn't yield great, but over that 50 years, they mined 800 pounds of potassium out of the soil. So you would think, man, there's nothing left, right? 50 years of no fertilizer. What happened to the soil test? It went up from 215 to 362. How in the heck did that happen? It happened because there's thousands and thousands of pounds of potassium locked up in the soil, and it became available. It actually went up more than where they fertilized. So this is just to illustrate the point. We don't necessarily have to step in and apply a product. So different sources, I just encourage people to look at salt indexes, try to use stuff that's more biologically friendly. And if it's not biologically friendly, try to add some carbon to it and buffer it so that it is. So how do you know if you can reduce fertility inputs? I'm just going to cruise through this. We do a whole bunch of testing. It's the bottom line. We look at aggregate stability, total nitrogen, Haney test, biomass test. We run a lot of PLFAs, phospholipid fatty acid, sap analysis, tissue testing. We're taking all these pieces of the puzzle. No one test is going to tell you everything you need to know, and we're putting them together to try to figure out what's going on in these soils. We got to do some testing. We got to run some trials. People ask me all the time, well, how much fertilizer can I pull out, or when can I do it? I don't know. We got to study that on their farm. So, do you need to buy these nutrients? This is the total nutrient digestion test I talked about. Do you all run any of these here in Canada? It's basically just super strong acids. You dissolve the soil and you see what all's in it. So if you look at, this is just a result from our family farm in northeast Iowa. Obviously your carbon, I did 0 to 6 in 6-inch increments down to 2 feet. I was just curious, what happens as you go deeper? So carbon and nitrogen, obviously they're going to drop as you go deeper. Your organic matter's at the surface. That's the way soil works. But look at phosphorus and potassium. Now this is going to vary depending on your soil type, obviously, and if you get into a different layer, but depending on your soil type, it may actually maintain or even increase as you go deeper. So we're standing on this giant reserve of nutrients under our feet. Now this is more of a philosophical argument or moral question, whatever, are you mining your soil if you don't put fertilizer out every year? Well, unfortunately, people don't live where food's produced anymore. All of agriculture is kind of a mining operation. If you think about it, You can dig it out of a hole in Morocco and ship it halfway across the world and apply it to your field, or you can use the stuff you're standing on. Again, you got to decide which is right. You're standing on a lot of stuff. That's what we're saying here. We got to feed our livestock. So this is not an exhaustive list, but everybody has livestock. It may just be under the ground where you can't see it. We got to keep these guys alive and going. Let's just say I wanted to wave a magic wand and I wanted to get rid of my biology or shut it down. How would I do it? Well, we call it farming, unfortunately. Pesticides, high salt fertilizers, tillage, compaction, poor grazing, all these things are going to inhibit our soil's ability to function. We run these PLFA tests. Simple one you can do. The math is a little wonky. Depending on the units, you're getting your report back. But it's roughly 1-to-1. Average PLFA, if I got a 2,500 on that, you got a couple thousand, maybe 2,500 pounds of biology per acre in the top 6 inches. And they need to eat. And it's your job to feed them. And they're going to eat before your crop does. So that's the way we need to think about what's going on underground. So just thinking about these things, like all this pain, these challenges we have, why isn't this going away? Why is it not getting better? You know, are you losing aggregates faster than you're building them? Are you killing your biology in the soil? Are you spending too much on inputs? All these different things that we fight with every day. So we just need to think about, like, why does my foot hurt? Well, we're really good at shooting ourselves in the foot sometimes and doing practices that are actually setting us back in the long run. So different things to trial. Here I'm just about out of time, but don't want to go through all this, but I just encourage people, don't use money or iron or technology to solve a problem that you can solve with biology, because almost always going to be cheaper and better in the long run if you can solve it with biology. Genetics is a huge deal, you know, just at least anecdotally, and it's almost a given at this point, I think, that a lot of our modern, you know, we call them racehorse hybrids or varieties, they're adapted to a super high input system. If you want to go down this regenerative route, more low input, you're probably going to need to look at different genetics. Plants are losing their ability to associate with mycorrhizal fungi when they're growing those, you know, high input environments. If you want your plants to get out there and get after it and work, you probably need some different genetics. Run trials, do some testing, you know, I really try to get people to stop just putting all their NPK up front, do some splits. You know, calcium, we overlook that. Readily available calcium at planting can sort of replace a lot of the, you know, visual things that we see with nitrogen. I didn't have time to get into composting or biofertilizers, but a lot of people are playing around with that. Just make sure if you're going to add anything, any biological, whatever, to your soil, you have to put it into an environment where it has a chance to survive. If your soil is compacted and anaerobic and you just write a check and throw a bug out there, probably not going to do a lot for you. So micronutrients and biology on the seed, I'm a big fan of that. Again, put it in an environment where it's got a chance. So just to wrap up, summary, it's all about the B word, biology. We need to have a different mindset, think about adapting to a more low input system ideally in the future. I know not everybody wants to go that route, that's fine, but stuff's not getting any cheaper. Fertilizer, oil, machinery, those costs are just going to keep going up, up, up. And the amount you get in your pocket as a farmer or the people that are helping support farmers is probably going to go the other way. So we got to think about how do we do this system differently and more efficiently. So that's all I have. I hopefully kind of stayed on time. I'm happy to take questions. I'll be around all day. How many of y'all think that was just completely nuts, everything I just said? You're laughing at me, so I'll take that at 50-50. Sure. I can figure out how to go back. I think it's this button. Oop. That one?
No, your very last one, your summary.
There we go.
Yeah, just with regards to Canada, more specifically PEI, unlocking nutrient value. If I were to tell you here that we don't reach 15 degrees soil temperature till mid-June, our most expensive row crops are about 120 days. But given microbial activity, mineralization,
Yeah, I don't know if you all heard the question. I'll try to paraphrase. Basically, a timing question. It's cold and wet in the spring. You know, do we need to think about how we approach this differently in this kind of environment where you've got a short growing season? I think, I mean, I totally get where you're coming from with that. Yeah, and to me, that's why even more so, I want to do the nutrients in season, because that's when the plant, you know, peak nutrient uptake is late vegetative, early reproductive for more crops. You know, so if we can get those nutrients out ahead of that rather than in the spring or even the previous fall, I think that's going to be a win. You know, we got a lot of data that backs up in season. And then, you know, the big challenge is your length of growing season here. Having that cover crop carrying over the year before and having a green plant out there can really help with that. You know, it can help get your water to infiltrate a little better, dry that soil out a little bit. Depends on your context there and how you manage that. I'll get into cover crops this afternoon, how we can kind of manage that water. But that's going to help keep that biological activity going, can actually warm up your soil a little bit. So, and there's things you can do in furrow to feed the biology in the furrow and also help warm that soil up a little bit, like early spring. But I wouldn't necessarily change what I'm saying here. It all gets compacted into a tighter window, if that makes sense. All right. I better get off the stage. I'm between you and break. So, all right, appreciate the time.